Okay, welcome to your first video lecture in section 10.2 on Fourier series. So when solving partial differential equations, one often ends up with solutions that can be expressed as an infinite sum of sines or cosines. So we found that in the previous sections on boundary value problems, sines and cosines played a crucial role not only in boundary value problems, but also eigenvalue problems that were also boundary value problems. So these trigonometric series are called Fourier series and are similar to Taylor series in the sense that we can generate a means of expressing complicated functions via simple functions like sines and cosines. In the coming lectures, we will explain how one can express a function as a trigonometric series, but to do so, we actually have to review the properties of sines and cosines. Okay, so the types of series we will study will be of the form a naught over 2, and then the sum of linear combinations of sines and cosines. So cosine of m pi x over L and sine of m pi x over L with coefficients out in front. Again, these are infinite series of such sines and cosines. On the sets of x's for which these series converge, they define a function whose value at each point is the sum of the series for that value of x. In this case, we say that the series that converges to that function is called the Fourier series of the function f. Some natural questions to ask are, what functions can be represented as the sum of Fourier series? This is very similar to the Taylor series question. And how does one compute the coefficients an and bn? So to discuss Fourier series, it's necessary to develop the properties of trig functions of the form cosine of m pi x over L and sine of m pi x over L, where m is a positive integer. The first property of note is that these functions are periodic. Okay. Recall that a function is periodic with period t if the domain of f contains x plus t whenever it contains x, and if f of x plus t is the same of f of x for every value of x. Note that if t is a period of f, then 2t, 3t are also all periods of f, and we call the smallest such t the fundamental period of f. So the idea of a periodic function is a function that sort of repeats itself every so often. If this is periodic, say with period 1, it's also going to be periodic with period 2, since this guy repeats itself every 2 terms, as does this guy repeating itself every 1 term. Okay, so here are some examples of some sine functions. I believe the blue is sine of pi x, whereas the orange is sine of 2 pi x, and the green sine of 3 pi x, just for a reference here. But those are the kind of functions that we're dealing with. It's important to note that linear combinations of periodic functions with period t are also periodic with period t, so there's some closure there. Further, it follows that the sum of any finite number, or even the sum of a convergent infinite series of functions with period t, is also periodic with period t. And the product of 2 periodic functions with period t is also periodic with period t. And so, when we're trying to construct series, it's nice to know that if all of the terms in the series are periodic with a certain period, that the series itself will also be if it converges. And so, as we said before, we're going to try to build functions from these cosine and sine, what are called Fourier basis functions, and they're all periodic with fundamental period 2L over m. And so we'll take the smallest of those, which is just 2L divided by 1, and note that all of these functions are thus periodic with period 2L. The other functions, so say cosine of 3 pi x over L, is 2L over 3 periodic, but it's also 2L periodic, for example. Okay. Additionally, in the construction of Fourier series, we need to describe an essential property of the cosine and sine Fourier basis functions that help us find the coefficients. And to introduce this property, we need to generalize another idea from linear algebra and calculus called orthogonality. Remember that 2 vectors were orthogonal as if their dot product was 0. Here we have to define a different dot product for functions, and hopefully you saw this in linear algebra. The dot product of 2 functions, or the inner product of 2 functions, u and v, on the interval alpha beta, is defined simply as the integral of the product of those 2 functions over the interval alpha and beta. And 2 functions are orthogonal if their inner product is 0. And a set of functions is said to be mutually orthogonal if each distinct pair of functions in the set is orthogonal. And what's really nice about our sine and cosine Fourier basis functions is that they're mutually orthogonal. If I take any two of the cosine functions and I try to take their inner product from negative L to L, I'm going to get 0 unless it's the same function. So the only time you can integrate two cosines of that type together and get something that's non-zero is if they're both cosine of n pi x over L. In that case, you get L. If you try to multiply the cosines and sines together, you're always going to get 0, so they're always orthogonal. And the same thing for cosine holds for sines. If you try to multiply two sine functions together and they have different indices, m and n, that inner product is going to be 0. Otherwise, it's going to be L. Okay, so in the next lecture, we're going to use this orthogonality property to determine the coefficients an and bn for a particular f. Okay, thank you.